That's cheat codes right there.
So here is where we get to mesh a few sections together. So we have talked about series, and we have talked about Taylor and Maclaurin polynomials. Now I want to talk about Taylor and Maclaurin series. Okay. What?
Is that recording?
Yeah.
Uh-huh.
Will this one end up on the list?
Hi, Matthew.
Who's Matthew?
Not here.
Hold up. But like, I mean, like,
Wow, that's sketchy.
Is he doing it
Okay.
or something?
So when we talk about Taylor and Maclaurin series, we know how to set up a Maclaurin polynomial, right? We find the function and evaluate it at 0. We find the first derivative and evaluate it at 0. We find the second derivative and we evaluate it at 0. And then we make all of these terms that look like this, and they're just going to continue on.
Yeah.
Okay?
Wait, why does it start using K and then like it keeps on going and then it goes to N?
Is that an 11?
Well, it says
Are the
from
parallel
K
lines?
equals 0 to N.
Oh,
What's
So we go to,
I'm gonna be
N.
honest. I low key assume that it's just an infinity.
okay? And then we do the same thing, but with, not centered at 0, right? Okay? I'm not telling you anything new here.
Yeah.
Right?
Yeah.
Well, now what we're going to do is now we're going to make these infinite. Okay, so we're not going to stop at n. We're going to plus ... They're going to be infinite. So instead of from k equals 0 to n, we're going to go n equals 1 to infinity, and we're going to write these series based on our polynomials, but they're going to be infinite polynomials. And then we can talk about intervals of convergence and radius of convergence and all of that stuff with our Taylor and Maclaurin series. Okay, so time out, real quick. The suspense is killing you, I know.
Oh my god, this is my
Yeah,
favorite
it's
part
to,
of the day.
it's to calibrate it.
This is your favorite part.
Some lag.
It's a pretty cool part.
Don't
yeah.
judge, Caleb.
Caleb could make a program that's
It's too
better.
short to listen to the words, so I go so long.
Make it in our
Okay, so really what we're talking about is just, okay, let's talk about the difference between slide number 1 and slide number 2.
That's 3.
Have you ever been to the eye doctor when they say, is it better the first or the second?
I know. And then it's the same. You're like,
Yeah.
yeah.
It says
Okay.
3 at the
Wait,
top.
so this is like the eye doctor. Which one looks better? The first one looks better.
Now we're going towards infinity. So like I said, instead of stopping at n, we're just going to say plus ... and we're going to keep going.
Oh.
Okay?
How would do that?
We are just going from a polynomial that ended at a certain place to an infinite series.
Yeah.
Okay? Do you feel like you need to write any of this down?
No.
Okay.
Alright.
Okay.
So f of x equals e to the negative 2x.
So why don't you just call it a Maclaurin or whatever?
Yeah, if it's centered at
If
0.
it's centered at 0.
Just
Just to irritate you.
I know a lot of these irritate.
why are there even 2 names?
Because
Yeah, why can't you just
Because
say
one was found before the other.
Oh, that makes sense.
So we're basically just like
Okay.
overwriting that guy's work and just applying it to Taylor. and saying
If
it's
f of x is e to the negative 2x, what is f of 0?
1.
F prime of x would be negative 2 e to the negative 2x, evaluated at 0.
Are we doing this infinitely?
Yeah.
Yes, we're going to do this infinitely. It might take us a while.
Is that
Or-
something-
We can find some patterns. So our second derivative would be 4 e to the negative 2x.
Negative 2 to 1,
Plug in 0 again. Okay. What's our next value going to be? Probably negative 8.
That's
And
what
then
I'm
talking about. Can't be
probably-
sure.
Good answer.
And then do you see where this is? I mean,
Can't be sure. Should probably check.
you keep going towards infinity, Richard. But we know that this is going to be 1 minus 2x plus 4 over 2 factorial x squared minus 8 over 3 factorial x cubed, and then probably 16 over 4 factorial x to the fourth. Okay. Let's generalize this. Well, we have x to the n, and we're always dividing by n factorial. Negative 1 to the n because we are alternating signs. And what else? 2 to the n.
So could we do negative 2 to
What do you mean good?
Same space. What I like to do.
When did they start using cube for this?
So our function is approximately, well, our function can be written as the series n equals 0 to infinity of, just for you, negative 2 to the n over n factorial x.
Oh, that's kind of nifty.
Just for you, negative 2x to the n.
I feel fine with sense.
I feel like we should separate that to
You can do whatever you want.
2.
Okay? Now, if I gave you e to the 3x, you don't think so? I think it would be-
Over n factorial.
Yes.
Yeah, it's just the
Three
3.
X.
Replace the 2 with the 3.
3x to the n over n factorial.
Okay.
Negative.
So I'm going to give you 3 series.
She said it.
Oh, it's
It's
just
just e
the,
to the
the
3x.
exponent of e. Why didn't you just like say
Because
that?
it's at 0.
Because I'm going to.
You said e
Right now.
to the 3x or e to the negative 3x?
There are 3 series that I need you to remember the patterns for, so that when we get to problems like this, instead of having to do this every time, we can just remember the pattern and maybe replace x with negative 2x. Or replace x with 3x, depending on what is inside our function. Okay? Oh, we're not going to do that.
What if it's like e to the 2 factorial
Then you would plug
or
2
like n
factorial.
n factorial x?
It needs to be a function. Okay? So e to the x.
Are you
We
saying,
know-
what is it? Actually,
Wait, are these all
Yeah,
assuming that they're recording?
Yes.
Okay.
These are all chlorine. Okay? So e to the
they're Taylor centered at 0.
Sorry, I'm trying to give credit to my man Lauren.
so e to the x has a derivative of e to the x has a derivative of e to the x has a derivative of e to the x, and all of them evaluated at 0 is 1. Okay? So when we create the Maclaurin polynomial, we have 1 plus 1x plus 1 over 2 factorial x squared, right? Blah, 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 blah. Where we can generalize it as x to the n over n factorial. Okay? So in our last example, all we could have had to do was take all of these x's and replace them with negative 2x instead. If we had e to the 1500x, we take all of those x's and we replace them with 1500x.
It's kind of excessive. But
Yeah, but you get my point.
I get your point.
Okay, now, cosine of x, its derivative is negative sine of x, and its derivative is negative cosine of x, and then we go to sine of x. So we have like this cycle of 4, right? Where every other one evaluates to be 0.
It's all
Right.
So just disregard those.
So, the cosine of x evaluated at 0 is 1. But then its derivative is 0. But then the second derivative is negative 1. And the third derivative is 0. And the fourth derivative is positive 1. And the fifth derivative is 0. And the sixth derivative is negative 1. And we get to the point where, okay, I think we can write this as a pattern.
Okay, let's do it.
Okay, so which powers of x do we have?
Evens.
We have all of the even ones. We have x to the 2n.
All of the multiples of 2. And 0.
We have negative 1 to the n because it's alternating, starting with positive and then negative, and then positive and then negative. And then down below, these guys match our powers. So 2n, the quantity factorial. Okay, cosine of x. If I say, hey, give me the power series or give me the Taylor series for cosine of 5x, all we would have to do is replace all of these x's with 5x.
Would these be different if they weren't combined?
Yes, because they would not be
I was just wondering if they like use roughly the same force series. Yeah.
okay, and then sine of x. What's going to happen here is we're basically going to get all of the other ones, right? The sine of 0 is 0. But then we get the first derivative to be 1. And then the second derivative is 0. And then the third derivative is negative 1. And then the fourth derivative is 0. But the fifth derivative is 1. And the sixth derivative is 0. But the seventh derivative is negative 1. Okay, so if we wanted to generalize these terms, are we still going positive, negative, positive, negative?
Yeah.
Chris, which powers of x do we have?
2n minus 1.
I would do 2n plus 1 because we're going to typically begin with n equal to 0. So I would rather not have the 2n minus 1. Okay. And what's true about our denominators? They're all the factorials that match the exponents. If you know these three, we can get a lot of things without having to do any work. Okay. And that's what we're going to kind of look at today. Is if I give you, like what can we do with these Taylor series? How can we work with them to help save us some time of not having to take derivative after derivative, and then generalize that pattern?
Yeah.
Okay, so this is a time saver for us. Okay. Do you think that you can remember the e to the x one?
Yeah, that's easy.
I mean, that one's not bad, right? And so then what you need to separate out in your mind between cosine and sine, which one are the evens, which one are the odds. And they have the same pattern as positive, negative, positive, negative. It's just cosine are the evens and sine is the odds. Okay? See what I mean? All right, so what can we do with Taylor series? We can substitute into a series for x. So that's kind of what I've already been talking about. If you have e to the 10x, you can take your series and replace x with 10x. Yeah. is it that you have to go to like so many board meetings, like public meetings? Is that AP?
That's government.
And is that something you take as juniors, seniors, sophomores?
Juniors, seniors.
Is anybody in that class?
Yeah.
Yeah. Have you gone to your public meetings?
No.
They're actually interesting.
I enjoyed them.
So did I.
Don't go to the major ones.
I actually
You have to get
talked
up
to
and
one of them.
talk.
Okay, you can multiply or divide the series by a constant and or a variable. Like x.
Went to a town hall.
I'll be at the board meeting tonight.
Or what?
Oh, we have to talk.
Let's pull up.
Wait.
Oh, They're all online, so we can just look at it later.
I want to pull up. What are you talking about?
The school board?
Yeah. So every school board meeting, like a different principal is asked to share something about their building.
Okay.
And so Mr. Johnson and Mr. Spilker are having the core department heads talk about the departments and like our PLCs.
What time?
7. 6.
It's public knowledge.
You can look it up.
You can add or subtract 2 series. I'm just curious if they can do it.
Let's go support.
I'm gonna go support our public school system.
Can we bring signs in?
Can we bring snacks?
We can protest.
What are we gonna?
Okay, Nick.
Is filibuster allowed?
Can you
Yeah, you can filibuster a school board member.
Okay, guys, I have this great new idea for the next Star Wars movie.
You can differentiate or integrate a series. And keep in mind that it may change. I don't need you. It may change the interval of convergence, but it's not going to change the radius. So, like, you would have to recheck your endpoints, but the radius of convergence will remain the same.
Is there more? I haven't written that.
There's a 5th one. You can do it.
I have to turn the page.
No, you just gotta find. There's always going to be room.
Okay, so this, and then the 5th one is what we did already. Recognize the series as a sum of a geometric power series. Okay, that's what you've already done.
When did we do that?
Friday.
Oh, right, that was the whole worksheet.
Yeah.
I have to do it in mountain.
Oh my god.
The little thing at the bottom. It sometimes it's the only way.
The only way.
You have 3 slides.
There are 3 examples
Okay, that's what I'm talking about.
that I'm planning on doing. I did skip over one, but I'm not sure if I really want to go back to it.
I'm gonna look. Why don't you look at the agenda of the school board meeting?
Oh yeah.
Okay.
Who is?
Is that
Is
where
it like
there's any?
socials? What's that?
Core.
Yeah.
Math, science, English, history, and then we throw in
So
special
it's
education
history?
also.
Who's the history?
Well, social studies.
Who's
Mr.
the-
Keller.
Oh, it's Keller.
So Mr. Keller, Mr. Gecki, Miss Homan, Dr. Hylock, and then Miss Judson.
And then who?
Miss Judson for special education.
Oh, okay.
All right. Example number 1.
Wait, that's the first example.
Write it down.
No, this is the second one.
But the first one after the notes.
The first example where we get to use our shortcuts. Okay.
Well,
Well, we know that the sign of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, blah, blah, blah,
Yeah.
blah, blah.
That's what we know.
X, whoops. -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. We know that,
Ew.
okay? So if I wanted the sign of x squared, we're going to take all of these x's and we are going to replace them with x squared.
Or we can just generalize.
Please don't try to get too ahead of yourself. Okay?
Do you have to go that far? Can you just generalize it after x squared?
Well, let me tell you. Sometimes it will ask you for the first three non-zero terms and the general term. Sometimes it'll just ask you for the series. Okay? So if it asks you for the first four non-zero terms and the general term, you would have to write all of this. Okay? X squared minus x to b over 3 factorial plus x to b over 5 factorial minus x to b over 7 factorial. And in general, our nth term is what they would call it. The nth term would be negative 1 to the n, x to the
4n plus 2.
ooh, good job. Over 2n.
We just leave it like the we just leave it like x squared.
You do need to rewrite it. Yes. Did we take a derivative? Okay, so be more specific about what about the table.
If you do the derivative to get from, for each one you do the derivative, right? You go with x squared, you get 2x in front.
So the sine of x squared, its derivative would be 2x cosine of x squared. And then you would have a product rule to do. And then you would have 2 product rules. And then you would have 3 product rules. So this is taking care of that.
That all comes. Okay, done. I'm good with that. Save you the work.
And a lot of it, yeah. Especially in that one.
Yeah, I don't want to have to do that. Even if you're not.
This one also. You don't want to do the product rule like once and then twice and then 3 times all for your derivatives. Right?
So what you do it?
What do we do? Caleb asks. This is x times cosine of x.
That's so great.
Chris used to work at Texas Roadhouse.
Yes, I do. I know there's a lot of people that work. You gotta be more specific.
She gave me
You did.
Last name.
How many Jeremys are at your work?
Okay, so we have x times the power series for cosine. Okay? And all we have to do is take x and multiply it through. So if we were to distribute this infinitely, we get x minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial. And then our nth term would only change. What's our power of x?
2n plus 1, yeah.
Oh, I thought
2n,
you-
this is x to the 2n times x to the 1st, so we add them together.
Yeah. So what changes?
It's just the
I don't
power.
like that.
it's the powers. Powers.
So since I multiplied x to the first to every term, x to the first gets multiplied to this guy, and it becomes
As
x
well
to
as
the
all
2.
the others.
What?
Oh, I just broke this and I regret it.
This is why we don't.
Oh,
really
okay.
Okay, so that's a good question. It all depends on what is asked of you. So sometimes it'll say write the first four non-zero terms and the general term. Okay. If it asks just for the series, then you could write n equals 0 to infinity of -1 to the n x to the 2n plus 1 all over 2n factorial. Okay. But I feel like you kind of have to work with this before you can write it like that. Do you see what I mean?
So you have to, or you can
I found this on the couch.
Oh, no.
How much money's in there?
Whose is it? Whose activity card?
Is it max?
It's a junior in my top class.
Let's make fun of him.
Is it
Is it
yeah, that's what I was gonna say.
Okay, so there are going to be times, Nick,
Yeah, that's a
where
guess.
no, you probably wouldn't have to do this, but there's going to be times where it is really necessary.
Yeah.
Sure, we didn't need that.
You just assume
Yes, you said his as well.
because you said
So you assumed his gender as well, so back
Well, I
up.
want to know is how long were you like
I
debating?
know, I'm fucking that.
Like, when did you get that?
I literally.
Okay, so you have this written down?
I walked up to the trash can to throw that away, and then I walked back and I saw it there.
Oh, okay.
Are you ready?
I'm
Like
ready.
to do this?
I'm
I
always
was
ready.
like,
Okay, so h of x. We have two series that we need to add together and divide by 2. So I'm just going to go ahead and divide by 2 by just putting 1/2 out in front. Is that okay?
That's okay.
All right. Now, our series for e to the x, we know to be 1 plus x squared, 2 factorial, plus x cubed, 3 factorial, blah, blah, blah. Okay, and we're adding that to e to the negative x. Okay, well, what would e to the negative x be? We would have to replace x with negative x. So 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial. Do you see why we're getting the alternating signs? Okay, every time we have an even power, that negative to a power doesn't matter for the even powers,
Gotcha.
right? So we have -1 to the n. Okay,
I can. -1 to the n.
x to the n over n factorial. Okay, now the general terms really aren't going to help us right now.
All right.
What's going to happen when we add these together? What is 1 plus 1?
That's 2.
Okay, but then what happens with x plus negative x?
cancel out.
Those go away. How about x squared over 2 factorial plus x squared over 2 factorial?
2.
We get 2x squared over 2 factorial. Okay, but then the cubes are going to cancel, but we are going to end up with 2x to the 4th over 4 factorial.
Well, they end up all canceling out.
Well, but we'll get there. We'll get there. But what's happening inside of our parentheses? What's happening with inside of our parentheses? We have 2 x to the 2n over 2n factorial. Right? We have all the even powers
Yeah.
with the even factorials multiplied by 2.
Alrighty.
So then Zane, what happens with the 1/2?
Well, it applies to the inside. And it cancels out.
They cancel out all those 2's. So when we distribute that 1/2 through, we get 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial. And our general term would just be x to the 2n over 2n factorial.
But what does that answer really tell us?
That's our series.
Like, what's the point of
You
it?
can plug that into your calculator.
And get an answer that means what? Like,
So we can approximate that equation.
so like an integral?
Yeah.
It's like,
Like we can plug into this polynomial, like we could plug 1/2 into this to approximate h of 1/2.
yeah, I
easy.
get that. But
Okay.
like,
What
what
would
if
that
you
look
if
like?
you if you like find the infinite like series of it, like the value? What does that like mean?
It's just more accurate.
But for like, what are you
Like,
finding?
what does it mean?
Like you're adding up each the value.
So, like, the more terms we add, the more accurate we get to the
Oh.
graph at that
I get it.
area.
But what,
So at x equals 0, this is that graph.
um,
So like, technically, if you estimated 1/2 in there and you did infinitely, it would be the exact answer.
so it kind of just seems like
Because it's infinite.
just like why would you ever want to go like if you had that in the real world? Why would you ever want to go to that? That just seems like
Yeah.
it makes it more difficult.
Because of our calculator abilities, is that kind of what you're saying? Because we have
No, I-
calculators and things to like help us as opposed to like a lot of
Yeah.
this came from not
Calculator.
having calculators.
Okay, that makes sense. Because you can plug, because if you plug 1/2 into that one versus into the infinite series, you're gonna get the same answer, right?
Mhm.
So that's just like before calculators were.
Mm,
How does a calculator calculate what we can't
How does
calculate?
a calculator work?
Is
You
there
know what I
a
mean,
on
though?
it?
Like, if you can't do it, how come it can? Kind of scary.